In this video, I'm going to discuss the sandwich theorem. This is also called the squeeze theorem, so you may see it by either name. This is a very useful theorem in helping us calculate limits, especially when we have a function that it's just very challenging to calculate the limit of if we have some known inequalities around it. So let's just jump right into it. We have the known inequality g of x is less than equal to f of x less than equal to h of x for all x in some open interval containing c, except for possibly at x is equal to c itself. And the limit as x goes to c of g of x equals the limit as x goes to c of h of x. If they're both equal to some value, we'll call it L. They're the same. Then the limit as x goes to c of f of x is also equal to that L. I'm going to break this down a little bit by little bit. So let's start with a picture. I think it's helpful to visualize this. So let me start. I'm going to draw one function. I'm going to call this function. If this is my low one, I'll call it g of x. This is going to be the lowest of the three. Then we have some other function, f of x. And it's between the third function and g of x. So the third function we'll call h of x. And so what I've tried to do is at this one point here, we'll call it x is equal to c, all three of these functions are kind of lining up. But, even short of seeing that, if we didn't know that right away, or we didn't know what that f of x was doing, what this is telling us right here is that g and h have the same limit value at some value c. Well, the only way, if that f is between them, the only way that's going to happen is if it's passing through that same point, right? If I don't have that green line, and I know at point c, f and if the g and h are meeting, if their limits are converging at the same point, and f of x is stuck between them, well, then it's going to have to pass through that point as well. So I think visually, once we see it, it makes a lot of sense. Now, what this does require us to know, it requires us to have an inequality, and it requires us to know that those two outer functions are converging to the same value at that point. Well, then we know the in-between value also converges. Now, I do want to kind of pick up on this on some open interval containing that c. It could be that, they are not always doing the same thing. So we might have our g of x that's sometimes higher and lower than the h of x. And so what we want to do then is we want to say, well, can we find some sort of interval around what I'll call point C? And let me stick my axis back on there. We'll call X and Y. I'll say I'm looking at C right here. Well, if I look in this yellow shaded area, maybe take it back a little bit more. This yellow shaded area, the blue is always smaller than the red, except for at that one point they're touching. Less than or equal to is fine. So we have found a small enough region. Now, if I were to continue out the shading, well, those flop. So why am I still allowed to use the sandwich theorem on some open interval? So can I find an interval over which g of x is always less than or equal to the h of x? Yes, I can. So I can apply the sandwich theorem to that region. How small or how big is it? We've kind of dealt with this before, and we're going to see this more in the class. We can make it as small as necessary. There has to be space on either side. So an open interval, there has to be space on either side. We couldn't say, look at this point, because on one side it's less than, on the other side it's greater than. So that wouldn't work. But if there's some space on left and right in which we can form this interval, that is good enough. So let's put this to use. Let's take an example. Let's suppose that we know the inequality -1/3 less than or equal to 2 minus 3 cosine squared over of x over 3 minus 2 sine squared of x less than or equal to 10x squared minus 1 over 3. Let's find the limit as x goes to 0 of that inner function and fully explain why we know that limit to be the case. So that inner function, I'm not saying we can't find this limit. It would be a bit of a pain. We will have some tools that will allow us to work with trig functions, but that would take a little bit of work, and it won't necessarily be real clean. There might be functions we just really can't find the limit of, or we don't have enough knowledge at this point to find the limit of. What I notice is because I have this inequality, I notice these outer two limits would actually be fairly easy to calculate. So let's do that. What I'm doing is I'm calling this first function the g of x. This middle one is my f of x. This last one is my h of x. Just kind of comparing it to the actual theorem. What I'm going to do is I'm going to take the limit of this first function. We want to know the limit as x heads to 0. So if we take this limit, very easily we get -1/3. I take the limit of the other outer function, and I'll look at the limit as x heads to 0 of the 10x squared minus 1 over 3. We can, of course, plug in the 0. We get 0 minus 1 over 3, which is a negative 1/3. And so we see that both of those outer functions are approaching the same limit value. Therefore, that inner function must be as well. So we can state the limit as x goes to 0 of 2 minus 3 cosine squared of x over 3 minus 2 sine squared of x is equal to negative 1/3. We know this because we know the inequality, negative 1/3, always to be less than or equal to 2 minus 3 cosine squared x over 3 minus 2 sine squared of x, less than or equal to 10x squared minus 1 over 3. And we found the limit of the two outer functions that is negative 1/3 and 10x squared minus 1 over 3, a little bit, to be negative 1/3. Therefore, the Sandwich Theorem tells me, the inner function, which is the 2 minus 3 cosine squared x over 3 minus 2 sine squared x, also has a limit of negative 1/3. This would be a complete answer. I know there's a lot of words there, but when we are using a theorem to explain something and we're asked to fully explain, we first got to do the work. We've got to show the math. We have to know the inequalities are true. We knew that was true because it was told to us, right? So we didn't really have any work to do there. We could prove it, with more work, but it's given to us. So we had that given. We calculated those limits, and then we're putting it all together through explanation. We're explaining that the conditions have been met, the inequality is met. We're explaining that the limits have been met, so all conditions are met, and then we're saying the theorem that we're using to arrive at a result. We're explicitly naming that theorem, so all of that needs to be there.